This is our last class, and in this class we are going to finish up lecture number 9 and also go over lecture number 10 as much as we can. Basically, in terms of the website, the only announcements that I have is I have put a new assignment, and this new assignment, assignment number 9, I'm not going to collect it. I just left it. It's a bunch of questions about lecture 10. This is like a guideline that you will do to prepare for the exam, really. So a bunch of questions. And I'm not going to collect it. So on top of this, I have written students do not need to return their answers to this assignment. It should be used as a guideline for preparation for the exam. Okay. And then you have your third project, which is due to the 2 days after the exam. So you have some time after the exam to finish that. Except that if you come to like course documents, up to last week's, I had this document number, lecture number 9, and then I had some supporting material for lecture 9. Now I have added some supporting material for lecture 10 and lecture 10 itself. Now, this supporting material that I have in here are not mandatory actually to read. The reason that I have left it, these are the sources. These are documents from IEEE 802.15. That part of, these are the, I have used more documents than these 3 references, but these are the 3 major ones so that you have some collection of like documents after the course. So you have some collection of documents in here, and you have some collection of documents in here. Here the documents are related to wireless LANs for lecture 9. Here the documents are related to WPANs. I left these 2 in particular because today the hottest topics in the wireless LAN industry are like security for wireless LANs, for example, high-speed wireless LANs, and things of that nature, which are supporting material in here. And also in WPAN industry, ultra-wideband is very, very popular. And actually there are 2 recent proposals as of last month that there are documents associated with that, and I have left those in here. The lecture that I have prepared also for 802.15 is a new lecture, and it covers material up to last month actually. So with that introduction, basically I would like to remind you that you are not responsible for reading documents in support of lecture 9 or in support of lecture 10. These are only for you to keep it for later on so that you have a complete set of documents for a variety of aspects of wireless industry, in particular wireless LANs and WPANs. With that, I will start my lecture, continuation of lecture 9. If you remember, lecture 9 was about 802.11 wireless LANs. And what I did, I went over, first I had the overview, but what I did in particular, I went over 802.11 reference model, MAC layer, and variety of physical layers. And at the end, I came at the performance, and that's when the time just was running out. And at that time, I said that I will pick up the issue of performance in this particular lecture. In addition to that, I just mentioned in the last lecture that the issue of performance is not only for wireless LANs, it's for WPANs as well, could be. For any local area network, there are certain issues related to performance which are actually not addressed in any particular book that I have ever seen. But in limited number of papers here, there, people have addressed that, and I'm trying to collect them and create something, which is performance analysis of wireless data networks, and in particular, wireless local area networks. I will, to start that, so we went over all of these material related to 802.11 and physical layers, MAC layers, then physical layers, and comparisons, etc. 802.11g. Here I had a sort of performance, but these are not the performance that I'm talking about, but these are just the data rates that you will read. And then I talked about HyperLAN 2, a comparison of performance of HyperLAN 2 and 802.11a. And that was the slide that I finished last week, talking about performance. Up to now, when I was talking about performance, for example, let's get something like this. We have like we have 8 set of data rates for HyperLAN 2 and 8 set of data rates for 802.11a. And what we do is that we see that under certain condition, for example, if I put them back to back, what is the effective data rate? Okay, this is a sort of like back-to-back physical layer. So the data rate is going to drop, for example, this is, HyperLAN, this is 802.11. If I put them even back-to-back, one line, I'm expecting to have like 54 megabit per second, but I receive something like 20 or 20-something megabit per second. If I go to HyperLAN 2, rather than 20 to 30, I will get something like 40 megabit per second. But this performance is like in a very controlled environment based on one user, this type of thing. Okay? There are other type of performance when I have multiple users. This type of performance, I will refer to that as physical layer performance. When I have multiple users, I will call it MAC layer performance. Okay? For example, other type of performance are something like this. This is for 802.11. You have seen similar curves in related to Ethernet, for example, or other data networks. Just comparison of Aloha and CSMA, etc. in medium access control lecture. In this type of performance, on the left-hand side, what you have is real throughput, either normalized to 1 or a data rate that you are going to observe, or the packet rate that you are going to observe. Okay? But basically what you have in this axis is the so-called load. Okay? Load means number of users, or traffic that number of users are generating. This type of performance, which has been typical performance. If you remember, for example, for Aloha, we had something like, for Aloha's, we had something like that. That peak was 18%. For like a slotted Aloha, we had something like that, was 36%. And then for like, I don't know, for CSMA, we had something like that, was like 70% peak. If you remember, in here I had like G, in here I had S. S was throughput, G was the offered traffic. Offered traffic is in a sort of normalized number of users, or number of packets which are generated by users, and this is the percentage of the packets which go through, or throughput. And the maximum of this throughput was 1. That type of performance evaluation, which is all the performance evaluations that you see in every book related to data, I will call it MAC layer performance. MAC layer performance. In all of these things, this type of networks, you're assuming your data rate is only 1. And that data rate is fixed. Okay? Means that if somebody said that throughput of Aloha is 18%, if your like data rate is 1 megabit per second, you say it is 180 kilobit per second peak. Okay? And performance is performance of a MAC. But when you come to wireless LANs or mobile data networks in general, your data rate is changing. Okay? That's one thing. Number two, the overhead that you have is very, very extensive. Because when you go, for example, to Ethernet, Ethernet doesn't have acknowledgement. And overhead is very small. When you go to like equivalent of that, to 802.11, you always have acknowledgement. In addition to acknowledgement, you are going to have heavy overheads. So there are two differences then, basically, between wireless performance of wireless networks as compared with the performance of wired network. In wired networks, number one, in all the analysis, data rate is assumed fixed. Data rate is fixed. This is one thing. But what will happen in the wireless? In the wireless, as I go away from the antenna, my data rate gradually drops down. Okay? As I'm walking in the building, the data rate changes. So how do you want to compare the performance? If my maximum data rate is 54 megabit per second, but I only cover half a meter, and you have 10 megabit per second, which covers like 200 meters, which one is better? That's one issue that we have in what? In the wireless, and we don't have it with the wireless. The other issue that we have, so the data rate is changing. The other one is that in wireless, overhead is more. Overhead is larger. Okay? Overhead is larger because, again, radio channel is a harsh channel. I always have to send acknowledgement. I have to put more protection for the, like codes, for example. Okay? So, as a result, we are talking about something different really for performance evaluation. When we went to the mobile, so wireless network, we have two types of wireless network. Huh? One was wireless WANs. Wireless WANs. Okay? For wireless WANs, if you remember, to calculate it, to evaluate the performance, we were taking this like cellular infrastructure, which means that we are assuming that the coverage is everywhere. Okay? And what we would do was that we would say that in one sector of antenna, for example, in this cell, this is the probability distribution function, cumulative probability distribution of signal to noise ratio, and then we will say for this signal to noise ratio, my data rate will have a cumulative distribution function like that, or it has a probability distribution function like this, and then I was taking the average of that density function as the average error rate in this sector. You remember? We did problems like that, and for example, we said like GPRS has something like 100 something kilobit per second in one sector. Okay, and when it goes to edge, it has 600 something kilobit per second available in this sector. This type of performance evaluation was unique. You never do this type of thing for what? Wired network. What you're doing in here really, you're giving the performance over the area. I refer to that as a spatial performance or a spatial throughput. Because you are assuming that a user is moving inside of a sector. And when he is moving inside the sector, signal to noise ratio changes, so the data rate changes. And you calculate the average of data rate. But you're assuming you have only one user. You're assuming you have only one user. If you have multiple users, you have an additional MAC overhead, which comes on top of that. That additional MAC overhead can be calculated from these curves like this, for example. Curves like this. Okay? But for when I come to like wireless data networks, my performance criteria is going to be a spatial, average spatial throughput in the area of coverage. When I talk about now wide area networks, and I say, for example, it is like 680 megabit per second per sector, means that wherever I go on the average, I have that. Okay? This is a wide area network. Okay? Now, how about wireless local area networks? For wireless local area networks, what we have one access point, and it has a coverage. We have a hotspot. If you go out of the hotspot, you don't have coverage. So if you want to take average over the entire area, doesn't make sense. Because you don't have comprehensive coverage. Okay? So as a result, how do you want to evaluate the performance? This thing has not been addressed. I haven't seen it in the literature, and I would like to, I will address to that in this particular lecture, how we want to do that. But to go there, I'm telling you, what I do is that I assume I have only one access point. And one user is moving in the area of coverage of that access point. This is one way to do it. And that's actually the way that you're doing that in your project as well. Okay? Now the point is that I have a user which is walking around one access point, area of coverage of one access point, 802.11a or 802.11g, what is the throughput, average throughput that he gets? And that's what I want to compare. And what I call that thing is, that is a spatial, average spatial throughput. Okay? So, if we come back to our overheads, what I have in here, I call it performance of the 802.11 MAC. This is like traditional carrier sense multiple access. With collision avoidance, I have another one which gets the carrier sense multiple access. Compare it with request to send, clear to send. If you remember, we have two different mechanisms in there in 802.11. Okay? But both of them are what? This one and this one are what? Are the throughput of the MAC, really. Okay? Including the MAC. Okay? Now I want to go for the so-called physical throughput. So I want to look at two issues. What are the two issues? Issue number one is overhead. Issue number two is what? Spatial changes in the data rate. Okay? To start that, this is overhead for the application layer. And these curves are coming from that MQP, and also it is the plots, some of the plots in here are coming from an MQP that I have referred that, and they are parts of your project number 3. Okay? So in a sense, I'm talking about project number 3 as well. Basically, if you have a packet of data and you're in the TCP/IP environment, you have the packet which can have the length up to 65K. Okay? Now, you take this, you put overhead, TCP overhead, like 20 byte, IP overhead, another 20 byte. Then you have LLC overhead, which is in two parts, for the snap and for LLC. Together about 8 byte. So this is logical link layer. And these are IP and TCP layers. Each of them, they have their overhead. 3 byte here, 5, 20, 20 byte in there. And then I have MAC header, which is like 30 byte. MAC for 802.11, in addition to the header, has some trailer, which are like error correction codes. On the other hand, when they are defining the MAC for 802.11, the length of the data cannot be more than, this is for frequency hopping, 2 kilobyte. So what will happen is that when the packet comes, which is 65 kilobyte, I have to do fragmentation. So one of the services that 802.11 provides, MAC provides, is fragmentation and assembly. And that's what we saw in the last time. So I have a bunch of overhead up to here. These are physical, this is MAC layer, this is logical link control, IP and TCP layer, overheads. Then on top of that, I put the PLCP. PLCP has two parts. One is preamble, one is the header, 18 and 6 byte. So I have 18 byte, 38, 20, and 20 overhead for each packet. And then I have like 4 byte trailing. The data is only in here. In your project, for example, the data is like, I think, 200 byte or 1000 byte. And then you want to see that if you add these overheads to that, what percentage of the packet is data and what is the overhead. But this is not the only thing that you lose. In here, you have acknowledgement mechanism. You have two acknowledgements. One is MAC acknowledgement. One is what? TCP acknowledgement. Okay? So you send a packet of data like here. How do you send the packets? You send the packets after interframe spacing. When you send the packet, everybody waits, and after SIF, which is the short interframe spacing, acknowledgement comes. This acknowledgement is what? This is your MAC acknowledgement. Okay? Then also the receiver sends a TCP acknowledgement after diff. Diff, if you remember, diff was the longer interframe spacing. Because this TCP acknowledgement is like a data acknowledgement for the MAC. But as soon as it comes to the sender, after CIF, a MAC acknowledgement for the TCP acknowledgement comes. So actually, with every packets of data, I have an overhead of 2 CIFs, 1 diff, 1 TCP acknowledgement, and 2 MAC acknowledgement. Okay? So if you include all of these things, with these overhead per packet, you are going to end up with a lot of loss. And then if you come, for example, in here, you see that effective data rate of like 802.11a or G, actually I have the G a little bit earlier than that. For the G, effective data rate is something like 25, 26 megabit per second rather than 54. Okay, means that even if you put the system back to back, your data rate is not going to be 54 megabit per second. It's like half of that. Okay, but if you put it back to back and you have something like hyper LAN, for example, since overhead is less, you have something like 40 megabit per second. Okay, and these are for other data rates. As you change the data rate, the ratio of these overheads will change. So with that introduction, I will go over the first part, first place of real throughput. So when people are talking about 11 megabit per second, 802.11b, you are not going to observe 11 megabit per second, even if you put it back to back. Okay, how much do you see they are reported in your project, project number 3? Okay, now this is the first problem, that I lose like 50% to overhead. What is the second problem? Second problem is that when I'm looking into the physical layer, if I take the throughput, this is throughput of a TCP application measured by a group of undergraduate students in WPI, okay, in a fixed location. So transmitter and receiver are in fixed location, and you're observing the throughput over time, okay? When you're observing the throughput, throughput is going up and down. What is the reason for the throughput to go up and down? Multipath fading. Because the channel signal to noise ratio is changing. Channel signal to noise ratio is changing. What will happen? The data rate changes. Because in 802.11, B and G, you have multiple data rates. And as the signal level, strength, comes lower than certain level, the data rate starts to change. So you have a bunch of data rates, and while you are sitting in one place, your data rate goes up. So how should I measure the, I mean, if I stay at the distance of 5 meters, how should I measure the throughput? I have to take average throughput. The same thing that I was doing for power. Power was fluctuating. I was getting the average of power. So in here, I get average of throughput. Now, if I get the average of throughput in distance of 5 meters, now if I go to the distance of 8 meters, what happens? Do I get the same average throughput? If I change my distance, what will happen? Data rate is going to be lower. Why? Because the average received signal strength is less, so I'm going to the lower end of the data rates. Is that right? Even if I move from 5 meters to another 5 meters, the same distances, I calculate the average data rate. What will happen? Do I get the same thing? No. Why not? Because of shadow fading this time. Okay? So the same stories that we had for radio propagation, which was multipath fading, shadow fading, and relationship with distance power gradient, we have it for throughput. Because as the power is changing, my throughput changes. Why changes? Because I have multiple rate of data. I have between 54 up to like 6 megabit per second. So as I move away, the data rate changes. Okay? Due to what? Multipath fading and due to shadow fading. So here comes the question. Then if I want to compare two things, if I want to compare like 802.11b with 802.11a, or G with the A, how should I do that? How should I evaluate the performance? One of the early methods that people were using, including our group actually, this is done by Intersil, for example. They take a typical building like this, and they identify locations in that. These are all locations. Okay? So they put the access point in here. They come to each of these locations with an 802.11a, and then they go with 802.11b to all of these locations. They calculate what? The data rate in all of these locations. Make sense? It's going to be different for, like, if I am 802.11a, I come in here, I have higher data rate. If I come in here, I have lower data rate. Okay? And in between something. If it's B the same, G the same. So when they calculated something like that, how do they get the throughput? They have this application layer software which sends TCP packets and counts the ones which are arriving. That's how they measure the performance. Huh? So then they create something like this. This is the coverage of 802.11a. The coverage, we have seen coverage like that for power. In here is coverage for what? For data rate. The same thing, the same concept. So I come to this building, my access point is in here. When I'm around the access point in this area, okay, I have 20 to 22 megabit per second. If I come to this area, I have 10 to 20. If I come to this area, I have 10 to 15 megabit per second. If I come in here, this area, I have 5 to 15 megabit per second. If I come to this area, I have 0 to 5 megabit per second. And in this area, I don't have any coverage. Here I am. Now I can calculate for the entire of this building, I can calculate what? Average throughput. And then I compare it, for example, this is for 802.11 with 802.11a, then with 802.11g, for example. Okay, so I can go to that building. For G, I have better coverage. I can see in that picture. If I go to, do you remember what was PBCC? Do you remember? That was the option for G. You remember? This is the coverage for that. And that one had only 2 data rates. And these are the 2 data rates associated to that. Now, I showed you these curves. If you want to look at these curves, these plots, they are very enlightening and very nice. But now somebody says, how do you compare the performance? You need to be quantitative. How do you want to be quantitative? You come, you create curves like this. You say in point 1, for example, this is the throughput of 802.11g, this is A, and this is PCC. And then at location 2 it is like that, 3 is. And when you look at all of them, you say, okay, when you look at all of them, in these locations that I have observed, 802.11g has a superior performance. In some locations, it is very much superior. In some locations, it's less superior. Okay? Okay, that's one way to do it. There are other ways to do it. What is wrong with this method? What is wrong with this method? It's very specific to this particular building, and it needs a lot of measurements in there. Okay? So another way to calculate this is again similar to coverage. Another way to calculate this is what? I come and I go to these locations, for example, in base station. Rather than to go to every location, I take like a line in here. I do 5, 6 measurements at different distances. Okay? And then I try to develop a curve which fits, which is in the old time I had distance power relationship. In here is throughput distance relationship. Okay? Do you remember? We had path loss equals to L0 plus 20 log of whatever. Huh? In here doesn't need to be 20 log, could be anything. But it would be a relationship between what? Throughput, S, as function of R, the distance. With limited number of measurements in one building, I can do that. When I do that, then I can come and create a function like SR. This function is what? Throughput versus distance. Okay? And this throughput versus distance covers between 0 to R. What is this capital R? That's the coverage of the access point. Okay? So what you do now, you say that, okay, if this function represents the throughput of 802.11a or 802.11b or 802.11g, what is the average throughput? If I look at this area of coverage, at any distance, which is a small r, at this area, how much is the throughput? S evaluated with this value of r. Okay? How much area it covers? It covers this circle. Is that right? So the area of r, this r, times dr, the data rate is SR. If I multiply it together, this is the total data rate in this area. Okay? If I integrate that between 0 up to R, the coverage is the total data rate per area. And if I divide it by pi r square is what? The total area. It's normalized throughput in the area of coverage. So I will call this thing average throughput over area of coverage. Okay? So I have in here this circle, which is 2 pi r times dr, that's the area, times SR. And then I have the total area, which is pi r square. The two pi's cancel each other. And this is my throughput. This is one of the parts of your project, actually, to be done. But this throughput is what? What is the meaning, physical meaning of this throughput? This throughput means that when I walk around an access point in the area of coverage, this is the average throughput that I observe. Okay? What is R? R is the coverage of the. Okay? So this is a measure that you are doing that. The functions for here and the measurements to find this function was done with the students, and they are given in the project. So in the project for 802.11, B and G, I have given you two different SRs. Okay? You can use that and find the coverage and average throughput for both of them. So that's one way to compare. This technology can be used for anything else. It can be used for raw data. This is the actual throughput for raw data. You remember how the raw data was working? You remember those step functions? As I go away, let's say in 802.11b, first I have a data rate R1, okay? And then I have data rate R2, then I have R3, then I have R4, and this is this step function if I do it. So I have these data rates. These are the coverage, these are the data. I have data rate of S1 at R up to R1, S2 at up to R2, S3 up to R3, S4 up to R4. I can apply the same equations for here as well if I want to find average spatial throughput. Okay, how should I do that? If R1 is from here to here, this area is the area A1, which is associated to R1. My data rate in this area is what? Is S1. Data rate in this area is S2. Data rate in this area is S3. Data rate in this area is S4. So what is the average data rate in the area? In here I have A1 times S1. In here I have A2 times S2. In here I have A3 times S3. In here I have A4 times S4. I add all of them together. This is the total throughput in this area. But I have to divide it by what? Area of coverage. What is the area of coverage? Is the big circle. What was the radius of the big circle? R4. So I have to divide it by pi times R4 square, which is area of the bigger circle. Okay? So what is this SU? This is now average data rate, really, if you want. Okay? No overhead. Overhead calculations, application overhead is not there. But this time it's just physical layer type of thing. So no matter what it is, if my data rate is changing as my distance is changing, I can use integral of this form and calculate what? Average throughput. What is physical meaning of that average throughput? Means that if somebody walks in the area of the coverage, we'll observe that average. In here is average data rate. If I do it for throughput, if I have function for throughput, it would be average throughput. Okay, these are the. This is the last thing that I wanted to mention about this lecture 9. So in summary, what I told you basically was that if you want to calculate the throughput of a wireless data network, if it has comprehensive coverage, means it covers everywhere, then you have to calculate throughput per watt per access point, or throughput per sector of antenna, throughput per cell. Okay, how do you calculate throughput per cell? You walk across that cell and you find the signal to noise ratio, probability distribution, signal to noise ratio in that cell. Okay, when you find the probability distribution function of that, you can map that to different data rates. Okay, and then you can get average data rate. That's when you have comprehensive coverage. If you have a spottish coverage, means you have one access point. How do you want to calculate the throughput of one access point? You find the average throughput in the area of coverage using what? Using this equation. And these things that I have is only for one user. And I refer to that as what? A spatial throughput, or physical layer spatial throughput. And this concept is completely different from anything that you have read about the throughput in the literature in other books or any other place. This is only specific to wireless data networks. Okay? And that's something new and very good to know for performance analysis. That was this last part of my lecture number 10. Do you have any question about it? If you don't have any question, while you work on on your project number 3, you will learn these things actually in more depth. Okay? Now we can take a very short pause, like a couple of minutes, just to change the tapes, and we start lecture number 10 immediately.